In this lesson, we're going to examine more closely how the cross product R cross P works out, the mathematics work out, to give us the correct velocity that leads to velocity and in turn momentum P that leads to the rotational motion that's going to occur in problems. So a little bit of an explanation up front here, maybe to give you a little better visualization of what we're looking at. So we have this top-down view, as I just underlined, of a situation where we're going to have a mass particle, point particle, come in with some velocity v. So it has no angular momentum, no angular motion whatsoever. It's just minding its own business, streaming along. It is going to hit the end of a bar, and it is going to stick to the end of the bar. This bar is pinned down such that after the mass hits the end of the bar, both the mass and the bar are going to stick together and swing in a circle. So let me just kind of maybe draw it here and maybe more realistic in terms of, so you have a bar, and you can think of looking at the top down. We're going to put a pin in here. So it's free to swing. That bar can spin in a circle. So our mass M comes streaming in. It is going to stick to the end of the bar, and then the two of them together are going to spin in a circle. So after the mass M hits the end of the bar, the only thing we have is rotational motion. Prior to hitting the bar, the only thing we have is linear motion. And we're going to see how R cross P is going to bridge that gap. It's going to connect the linear motion of the point particle, mass M, to the angular motion that the bar and the mass are going to have after the collision. Well, let's see how it does that. So part of what we're doing here is understanding, using our knowledge of the fact that circular motion will occur after the collision, to actually assign an initial angular momentum to the purely linear motion that is present prior to the collision. So we have a collision. We're going to talk about conservation of angular momentum, which I'll get to in a moment. But first, we're going to give this assigned value, which is R cross P, R cross MV, and let's see why that works out. Hopefully it will make sense, because I think this is somewhat intuitive in terms of what would have to happen for a mass M to hit the end of the bar and spin it in a circle. Well, the R cross P and MV, as we said on our previous lesson, right? So that's the P vector, if you want to put that in. R cross MV, the V sine theta gives us just the tangential part of that initial V. So just the part that is going to correspond to the speed that is going to be part of the rotational motion when the bar and the mass spin in a circle. The V radial, the V cosine theta, notice whatever component that initial velocity had that was along the bar, none of that velocity and subsequent momentum will contribute to rotation. So just like if you remember for torque, it wasn't radial forces don't generate rotation, radial momentum won't generate rotational momentum after the collision. Had the mass just streamed in from out here, right? So you don't have to draw this in, but had the mass just streamed in radially and hit the end of the bar, it just would have stuck to the end of the bar and there would have been no rotation. So cross product picks out the part of the momentum that will be present after the collision as part of the rotational motion and rotational momentum. So that L initial is really an assigned value, and we can see that our cross product even gives us the correct direction for the rotation when we do our right-hand rule, our cross product. We would do R cross mv, that's going to be a thumb out of the paper, positive z hat, which is a counterclockwise rotation. So it matches up perfectly. We know that from our last chapter, matching up our equations to our linear equations, that sum of the torques external equals delta L over delta T, just like sum of the forces external equals delta P over delta T. And just like for collisions that we've studied that were linear XY collisions, we assume there were no external forces during the collision because the delta T, we are saying, is so small during a collision. As soon as you see the word collision, collisions by definition conserve momentum, both linear momentum and now we see angular momentum, because there are no external forces, no external torques that are allowed to act over that very short time period. So we're going to do more with this in our next lesson and look at a numerical example, but before we leave this lesson, just a very quick look at how R cross P for point particles. Remember, we use L equals R cross P for point particles, and we're going to use L equals I omega for extended bodies. But to just see that R cross P is consistent with all of the structure of the mathematics and physics we're using up to this point, let's take a very quick look at what is here. There's no new equations, just some quick math. We have L equals R cross P, and there is no reason mathematically that you are not permitted to simply take the derivative of both sides. As long as you take the derivative of both sides, you are being consistent. So here we have dl dt, and we want to see what dl dt is going to equal. Well, cross product is a product, so we can use the product rule. And we have first times the derivative of the second plus second times the derivative of the first. dr dt is v. V cross v is 0, so we lose the second term entirely. dv dt is acceleration. So when we bring the m back in with the a, we get ma, which is R cross MA, which is R cross F, which, look at that, torque. So dl dt equals torque. Now, we knew that, but this was just a proof. You won't have to prove it either for our test or for the AP test. But it shows that even for point particles, conservation of angular momentum is going to apply. The sum of the torques equals dl dt will also be valid for point particles in those collisions. And as I said, our next lesson is going to be a specific numerical example that hopefully will give us a better feel for how these types of problems work.